Tunnel boring machines, TBMs, also known as moles, are used for constructing tunnels with circular cross-sections through different types of soil and rock strata. These machines are significant for underground tunneling operations and are commonly used in civil engineering projects such as railway and highway tunnels, water and sewage tunnels, and even mining operations. In essence, a TBM provides an efficient, safe, and environmentally friendly way of tunneling, making it a fundamental part of modern tunnel construction. TBMs were first designed in the mid-19th century, with the first boring machine patented by Marc Isambard Brunel in 1818. The machine was used for the construction of the Thames Tunnel in London. Since then, technology and engineering have significantly improved, creating TBMs with high performance and operational efficiencies. TBMs can vary in size, with the diameter of the cutter head reaching up to 17.6 meters, making them suitable for various tunnel diameters. TBMs are composed of several primary parts, each serving a unique function. The cutter head is the foremost part that comes into contact with the soil or rock. It is equipped with disc cutters and scraping tools that break down the soil or rock during tunneling. This part of the machine rotates, exerting pressure on the excavation face, which in turn fractures the rock. Behind the cutter head is the shield, a large metal cylinder that supports the excavated tunnel until the permanent lining can be installed. The shield also protects workers from falling debris and from potential collapses of the tunnel. Moreover, it houses the drive systems that rotate the cutter head and push the machine forward through the ground. The conveyor system is another critical part of a TBM. As the cutter head breaks down the soil or rock, the excavated material falls onto a conveyor belt system that transports the debris from the face of the excavation to the rear of the machine. From there, it can be moved out of the tunnel through additional conveyance systems. One of the remarkable aspects of TBMs is their versatility. There are several types of TBMs designed to work in different geological conditions. The Earth Pressure Balance, EPB, TBM is used in cohesive soils and soft ground conditions, while the Slurry Shield TBM is used for tunneling through water-bearing soils and rock formations. The Hard Rock TBM, as its name suggests, is employed for hard rock formations. The operation of a TBM requires a carefully planned process. Before tunneling begins, a launch shaft is typically excavated at the starting point of the tunnel. The TBM is then lowered into this shaft and assembled. Once the TBM is operational, it starts boring into the ground, with the excavated material removed via the conveyor system. As the machine progresses, a new section of the tunnel is simultaneously supported with concrete segments to prevent collapse. One of the advantages of using TBMs is their speed and efficiency. They can excavate tunnels far more quickly than traditional drilling and blasting methods. TBMs can achieve tunneling rates of several meters per day depending on the type of ground conditions and the size of the TBM. In addition, TBMs cause less disturbance to the surrounding ground, reducing the risk of ground subsidence. Furthermore, TBMs improve safety in tunnel construction. Working inside a TBM's shielded environment, operators are protected from the risk of ground collapses and falling rocks. TBMs also mitigate the health risks associated with traditional tunneling methods, such as exposure to dust and explosive gases. However, TBMs also have their limitations. Their large size and weight make them difficult and expensive to transport and assemble. TBMs are also more susceptible to breakdowns in harsh conditions, which can lead to delays and increased costs. In addition, the removal and disposal of excavated material can present logistical challenges, particularly in urban environments. Over the years, there has been a significant development in TBM technology. For instance, the introduction of TBMs equipped with sophisticated navigation systems has revolutionized the tunneling industry. These machines use GPS-like technology to guide the TBM's path, allowing for precise control of the tunnel's alignment and grade. Another significant advancement is the development of hybrid TBMs, capable of switching between different operating modes to cope with varying geological conditions. These machines offer enhanced flexibility, allowing them to navigate complex terrains with ease and efficiency. Moreover, the future of TBMs looks promising, with new technologies being developed to further enhance their performance. For instance, researchers are working on improving cutter technology to increase the machine's ability to cut through harder rock and at faster speeds. There are also efforts to develop TBMs that can repair themselves in case of damage, reducing downtime during tunnel construction. In summary, TBMs play a critical role in modern tunnel construction. They offer significant advantages in terms of speed, efficiency, and safety over traditional tunneling methods. With advancements in technology, TBMs will continue to be instrumental in shaping the infrastructure of the future. From subterranean transit systems to underground utility networks, TBMs will remain at the forefront of underground construction. In spite of their limitations and challenges, the contribution of TBMs to the realm of civil engineering is undeniable. They have transformed the way tunnels are constructed, enabling large-scale infrastructure projects that would otherwise be unfeasible or extremely hazardous. As engineering and technology continue to advance, it will be fascinating to witness the future developments in TBM technology.